Hello, grade 11 A-level students. Right now we are going to study about the continuation of the reaction in benzene. This is still about electrophilic substitution of benzene molecule. The third part is alkylation or called Friedel-Crafts reaction. Okay, Friedel-Crafts reaction is actually using the catalyst aluminum chloride alkyl group attached to the benzene ring. So aluminum chloride is called as Friedel-Crafts catalyst. So from the reaction of bromination, chlorination, they are called as Friedel-Crafts reaction. In this one, the Friedel-Crafts reaction is using the CH3 or methyl. So substitute the hydrogen with methyl group in order to become methyl benzene. The other name of methyl benzene is toluene. Okay, there are some reactions. The reaction goes via formation of intermediate carbocation. Intermediate carbocation, the purpose of intermediate carbocation is to form the electrophile methyl. This methyl will attract to the benzene that makes the benzene donate its electron to the methyl, and then the methyl will make a covalent bond with the benzene along with the hydrogen, and then the electron of the hydrogen is taken by the benzene in order to restore the stability of benzene molecule. And then after that, after the alkylation, and then there is a second acylation. Acylation, it is from the word acyl. Acyl comes from the acyl chloride. Acyl chloride is also a chloroalkane in Friedel-Crafts. It is used to make phenyl ketone. So this is the combination between benzene and a ketone. This one, acyl chloride is a derivative of carboxylic acid. The reaction between acyl chloride and aluminum chloride as the catalyst produce acylium ion. This acylium ion is the strong electrophile. Okay, so the intermediate from the attack of the acylium ion is on the benzene ring. So this one acyl chloride, in the presence of aluminum chloride, it will become acylium ion, an electrophile, and then it will form AlCl4. This one, the electron of the carbon here is taken by the electronegative chlorine. That makes the chlorine become negative ion. This one will become positive ion. So the positive ion is called as acylium ion. This one, the Cl negative, has an extra electron. This extra electron can make a dative covalent bond with the AlCl3 that makes AlCl4 negative. And then the benzene make dative covalent bond with the positive carbon. And then that makes the positive carbon, the acylium ion, make a covalent bond with the benzene. Also there is hydrogen. Just like in the reaction of acylation and reaction of bromination, and then also with chlorination, also with nitration, the hydrogen will be out from the benzene or will be displaced by the presence of acylium. Okay, next let's continue this one, electrophilic substitution in substituted arenes. The orientation of the incoming group. The orientation of the incoming group, this is basically for the second functional group. So in here, when methylbenzene is treated with nitric acid and sulfuric acid, the three possible mononitro compounds are formed in the following ratios. So in here, it means the sulfuric acid is only a catalyst to make the strong nitrate electrophile. This one, nitromethylbenzene, nitrotoluene. This is also nitrotoluene. This one also nitrotoluene. Now, this one, as we can see here, the toluene or the methyl is located in carbon number 1 of the benzene. This one located in carbon atom number 2. We count here based on the clockwise. Why clockwise? Why is it not anti-clockwise? Clockwise because the shortest of the branch of the carbon atom that has the other functional group. And this one is the number 3 carbon atom. And this one is in the position of carbon atom number 4. And then, so that's the reason here we know that in NO2 when react with toluene, this is 58%, 38%, this one 4%. 4% means less likely to occur. 58 and 38 more probably to occur. So if the nitrate electrophile has attacked the ring in the purely random way, the distribution should be 40-40-20. There being 2 into the second carbon atom position and 2-3 position, but only 1 for position. This non-random attack is seen in the other reactions too. Let's see this one. Ortho, meta, para. Ortho means in the position of 1 and 2. This one, meta, is position 1 and 3. Para is position 1 and 4. So this one, this one we see this one. It is ortho for bromine into the methylbenzene. It would probably in the position of 1 and 2 as much as 33%, and then para as much as 66%. And then this one, the ratio ortho and para. So it is in 99 to 1 ratio. So if there is bromine attached to this one, to the toluene, so it probably in the position of 2-4. That's the meaning. Okay, also the same with the nitrate. It is in the position of 2 and 4. While if there is NO already in the first, as the first functional group, and then the second nitro will substitute hydrogen in the benzene. The second nitro will be in the position of 3. Okay, so and then here, when there is a carboxylic acid and then the nitro, it would probably in the position of 3. Okay, let's continue with this one. This rule applies for the structure of benzene whenever there is the first functional group already. So this is the how to know which second functional group should be substituted in the benzene ring. From here, from the data in table 25.5 can be interpreted as follows. The orientation of the incoming of the nitrate and bromine depends on the substituent already in the ring, not on the electrophile. Okay, some substituent favor both 2 and 4 position, whereas the other substituent favor in the 3rd position at expense of both 2 and 4. If we look closely at the type of the substituents, there are 2, 4 directing. We find that either they are capable of donating electron in the ring by the inductive effect, or they have a lone pair on the atom joined to the ring. This lone pair can be incorporated into the pi bonding system by sideways overlap of p orbitals. Okay, so this one, we have to look at the availability of a group of ion or polyatomic ion, whether it has a pair of electron that able to make dative covalent bond, or in the presence of inductive effect. Okay, let's see this one. On the other hand, all those substituents that favor 3 substitution have a dipole positive atom joined directly to the ring. So this one, position 2 and 4 directing substituent, what are those? It is the methyl, and then it is the hydroxyl, and then next one it is in the amine, and then in the 3rd directing substituent it is nitrate, and then this one, what is this one? Aldehyde or ketone? This is called as aldehyde, and then there is a cyanide. Why is it like this? Because this one, the N is positive, so this Ar means arenes. The arenes give the electron to N to make itself stable. Similarly with this one, the arene give electron to the carbon of the cyanide, and then this one is for the ketones. Okay, let's see this one. The orientation effects of different substituent we are going to study in the next meeting.